Okay, hello everyone and welcome to this talk about the future. My name is Robin and I'm a PhD student from Belgium. I've been working with the protocols for 4 years now and I'm also a contributor to the QUIC and HP3 standards. I will list some of my own work, but I also have some from others and I always list my references as I am a good academic. Before we can look towards future though, we first need to travel back in time. Don't worry, not too far, just 4 years to the introduction of HTTP2. A lot has changed, a lot has happened in that time, and according to the latest numbers, we are now at about 50% of all pages are served using H2, which is quite nice. And I think it's about time that we look back at what we've learned in that time and how we might optimize these deployments. First thing I wanted to talk about was that a couple of months ago, a team from Netflix found a couple of security vulnerabilities in H2 implementations. Now don't worry, nothing critical. It's not like there's a remote code execution in there or something. These were all denial of service attack factors. Still, they impacted a lot of high-profile implementations. All of these were vulnerable to at least one of the problems. So if you hadn't heard about this, or you're quite slow in updating your servers, maybe that's something to look at. The funny thing is that I am myself implementing an HP3 server at the moment. And when I saw this come out, I was like, well, duh. Obviously, these things are security problems, and any programmer worth their salt is going to solve them immediately when implementing the protocol, right? So I went back, checked my code, and of course, I'm vulnerable to about 6 of these. So there's definitely a difference in what you know might be a problem down the line and what you decide to implement in the initial go. The second thing I want to talk about is HTTP2 server push. This is one of the main big new features in H2. And one of the problems it solves is that if you load an HTML file, then you might then discover that you also need a style sheet. And when you've downloaded that, you might see, oh, I also need a font. And so it can take quite a few round trips before you actually discover all the resources you need. So with push, in theory, we can send all of that down with the HTML in one go, saving some round trips. I said in theory because in practice, it's not that simple. Push is limited by the amount of data it can send. And this is because H2 runs on top of TCP, and TCP is limited by congestion control. If you don't know this, in a new TCP connection, you can't simply start blasting data full speed because you might be overloading the network. So the only thing you can do is actually start quite slowly. Typically, that's about 14 kilobytes or a low multiple of that. You send that out, and then you have to wait for acknowledgements from the other side before you can actually improve your send rate and up your congestion window. So this means this initial round trip for push, you're limited to, let's say, 14 kilobytes. This means if your HTML is larger than that, which most of yours probably is, you won't see a lot of benefits from push, at least in this case. And there are many other problems with push. For example, you might be pushing things that the client already has in its cache. This is because there is no way for a server to know what a client already has. There used to be a proposal for this. It was called cache digests. But it turned out none of the browsers was actually willing to implement that, and that was declared dead a couple of months ago. You can implement something similar yourself, but it's a little bit finicky. There are other problems. Not all browsers support all use cases, and you can only push on one connection and those kind of things. This has led to the fact that only about 0.5% of all web pages that do H2 actually also push some of their resources. And so there have been some people that have been advocating, let's just cut push completely from HTTP3. Now, I'm very happy that has not happened. Push is still in there. And I'm happy because I think push definitely has potential, just not for this use case. There are two where I can see it being very beneficial. The first one is if you're using a CDN. So let's imagine you have an edge node close to the user, and the user requests an HTML that you have to fetch from the origin. While you're waiting for that to come back, you might have what you might call idle time at the CDN edge node. So you can decide to start pushing some of the stuff that the CDN is cached during that idle time. This will then hopefully increase the congestion window between the client and the edge, and by the time your HTML comes back in, you might be able to send it immediately in full. And then the browser can start rendering at least the critical stuff in one go. So this is definitely interesting. And Akamai has actually a product around this. It's called Adaptive Acceleration. And they try to do some stuff with machine learning in there as well. So they try to predict how much idle time you actually will have, and then they look at which resources are most beneficial to push in that time. All of that automatically, and they're getting some pretty cool results. Now, the second use case I want to talk about is, how about we don't push at the start, but during the page usage. We now have things called single-page applications and also native applications that don't really load new pages. Instead, if they have new content, they use REST APIs or JSON APIs. And those JSON responses typically also have some sub-resources. Typically, let's say, images, or if you're using old-style REST, even other JSON resources. And I think these things are actually prime examples of things that you can push, because by now, your TCP connection has been warmed up, so you have a nice large congestion window, and you might be able to send all of that down in one go. And this plays very nicely into the trend that we see towards things like edge workers, where you can intercept these responses at the edge, see what you might have to do, and try to push some of that out. So I think this is a very interesting use case, but I haven't actually seen that many people use it in practice, and I cannot figure out why. So if you have done this, and you have some problems, please let me know. And if you haven't done this, and you have a lot of REST stuff, please try it, and let me know, okay? The next thing I want to talk about is prioritization. You might know that if you use HP1, you actually have to open multiple parallel TCP connections, because each one can only carry one HTTP resource at a time. That's like the main improvement from H2, right? We can now do all of that on one connection, much more efficient, because we are now multiplexing things. Now, when I say multiplex, you probably start thinking about something like this. You cut up your resources into smaller bits, and then you put them on the wire one after the other, interleaved, so the resources share the bandwidth. Right? That's definitely one way of doing it. Let's call that incremental delivery. But you can also imagine other ways. For example, we can send things sequentially as well. Send each resource in full, back to back. And then we can progress and we say, how about we mix the two? We send some of this sequentially and some of this incrementally. And when you take this to the absurd, that's when you get my research. And then you get this kind of graph from our latest paper, where each of the rows is a different way that you can send the same web page to your browser. Right? Now, why do we need all this variety? It's because this system in HTTP2 is extremely flexible. It allows you to do a lot of things. And it's very clearly to see that in the Firefox implementation of this. So in H2, you build what is called a dependency tree, where each of the leaf nodes of the tree is one of the resources on the web page. And the composition of the tree, the way it looks like, actually describes how you would like the bandwidth to be distributed across these resources. Now, flexible system is good. It also means that nobody really knows how to best use it. And this is very clear when you look at what the other browsers are doing, because nobody agrees on what the best approach is. So Chrome and Safari and Old Edge are actually doing the complete opposite of each other in this case. They didn't know it back then, but apparently we have tested this, and it turns out that Safari and Old Edge are actually doing the worst case. They can be up to 50% slower than Chrome. And this has now also been confirmed by Google and Facebook recently. Now you might think that's already weird, but it gets worse. Because this is just the browsers. And this is what the browser outputs, sends it to the server to tell it what it wants the server to do. That doesn't actually mean your server is going to listen. And Andy Davies and Patrick Meenan, they tested some CDNs and some hosting providers. And they found that only 9 of them actually do this correctly. That doesn't mean that the rest is 50% slower. That just means they leave some performance lying on the table. Some of that is because of implementation bugs, because a flexible system also means very complex to do right. But there's another problem, which is introduced by what you might call buffer bloat. I have an example to explain that. Let's say that we have a typical setup of an origin server fronted by some kind of a cache. And we get 4 requests from our client. The 2 top ones are very high priority, but not cached. The bottom ones are low priority images, and they are cached. But what you might want to happen, ideally, is have the cache start sending some of that image data while it waits for the origin, but interrupt that immediately as the high priority stuff comes in so that you get that first. What ends up, or can end up happening in practice, of course, is more like this. If you have very large buffers in between, the cache might think, oh, I've got room. I'm going to just put everything that I have locally in there because that's good for efficiency, right? And so you end up not having room in the buffers for your high priority stuff anymore, and you get what you might call a priority inversion situation where you do the exact opposite of what you wanted. So all of this is a mess because even if you have a well-behaving origin, you can still get bad prioritization behavior because of complex setups. And I promised myself, Robin, you are not going to use memes in this presentation because you are a grown-up, damn it, and this is a serious conference, but I just couldn't, you know. I've been studying this for 3 years now, and it still flabbergasts me how complex such a relatively simple aspect can be in practice. Now, what can you do about this? First, I would say confirm that you have this problem. I would say use web page tests. If you run your page through that, you're going to get, amongst other things, this kind of a waterfall diagram, where each row is one of the resources. And recently, they added, what you can see there, the opaque bits in each row. That is where the HTTP2 data actually came in for that resource. So now you can see if low priority stuff is arriving before high priority stuff. If you find out you have a problem, the solution is simple. Simply switch CDNs, right? Or maybe that's not very realistic. What you might be able to do is to tweak some of your settings. You might be able to tweak some kernel buffer sizes, sometimes application layer stuff too. If the problem is in network buffers, you might be switching to BBR congestion control, which is in most recent Linux kernels as well. I think, though, the best approach would be to simply use a server that does not listen to the browsers. It simply ignores what the browsers say and just tries to do something optimal itself. For example, Cloudflare has a commercial offering now on their CDN that does that, and they're getting pretty nice results. Finally, be aware there is a bug in Chrome if you use preload, where if you have the preloaded resources, they can actually be sent before your critical resources. And that's exactly what's happening in the screenshot there. The red stuff is preloaded fonts, and they are being sent before the green stuff, which is your critical CSS. So again, you might actually want to have that the other way around. Now you might be thinking, I am not on H2 yet, and seeing this, I don't really want to switch. Maybe I can just wait for H3 and skip H2 at all. You might be laughing, but I actually heard people saying that a couple of weeks ago at another conference. And I would say, do not do that. That's terrible. I think this is actually a good thing. This means that people are starting to look into H2, starting to get some experience with it, starting to find the best practices. This means the protocol is maturing. And I think we will go through a very similar period with HTTP3 as well. I'm immediately going to partly contradict that statement, though, because we looked at all of this complexity, and it turns out we really don't want to support that in H3 anymore. So the HTTP2 priority system has been completely removed from H3. We are not 100% clear yet what the replacement will be, but this proposal is the one that is most likely to win. It simplifies things a lot. It's now just a simple HTTP level header with 7 layers of priority, and 1 Boolean to control if you're sending things incrementally or not. We hope that this simpler design will lead to less implementation bugs and easier debugging in practice. And with that, I have built myself an incredibly smart segue into the next topic of today's talk, of course, those future protocols. I'm not going to linger too much on the new features that they provide. I'm mainly going to focus on the deployment challenges that they may pose. But first, I feel we need a little bit of introduction to keep everyone on the same level. So what is QUIC? QUIC is a new transport layer protocol. What we really wanted was a better TCP. But TCP is too popular. It is implemented in billions of devices on the internet, which means if you try to change anything about it, things are going to break at scale. So the only way forward in practice was to define something new. You can't do something completely new, because devices also wouldn't understand that. So QUIC uses UDP as kind of a substrate. And on top of that, it actually implements all the features that we know and love from TCP. This means QUIC is reliable, it is in order, it has flow control and congestion control. It even uses TLS embedded as its encryption layer. It is, however, not a full drop-in replacement for TCP. And that is something we noticed when we tried to run HTTP2 over QUIC. So we did need a few changes on that, and that new version is actually what became HTTP 3. Now, I think it's actually a bit of a misname. I think they chose that name mainly for marketing purposes, because I think the step from 1 to 2 was way larger than from 2 to 3. Not that much has actually changed. Most of the functionality from 2 is still in 3. You won't notice that many differences, at least at the HTTP layer. You will see differences in the behavior, of course, but that's mainly because of QUIC, not H3. The other thing you need to know about QUIC is that it actually encrypts the transport layer. With TCP, a lot of this is actually plain text. TCP header can just be viewed on the network. That's exactly the big problem, because you have middle boxes that actually parse TCP and then implement features on top of that, for example, network measurements, or if you have firewalls, certain security features. That means if you, again, try to change TCP, those middle boxes are going to complain. So with QUIC, we really want to have something that can keep evolving over the next decades. And so we decided we're going to encrypt all of that. If middle boxes can't see what's there, they can't use it, they won't rely on it, and if we change it down the road, nothing much will break. And that sounds good, but it's obvious that there is a sort of tension between the middle box creators and QUIC, right? And that's, I think, the first big deployment challenge for QUIC is that I think a lot of networks will be blocking QUIC because of this. There have been several studies on this again, and some of them say that actually there is a considerable part of today's internet that actively blocks QUIC and or UDP. And I think that might only increase as we see more QUIC traffic. For example, this is a quote from one of the firewall vendors not too long ago. And they actively recommend their users to block QUIC because it says security is more important than any benefits you might see from QUIC, at least until we're able to update our middle box to add the security features back in. The problem is, I think, that is not going to happen. To give you an example, I've heard that some companies actually intercept their encrypted traffic from inside a company. They decrypt it to do packet inspection and to do things like antivirus. What they then do is re-encrypt it with some kind of a company internal root certificate to stop browsers from breaking. And I talked about this with David Shinazi, who is one of the engineers on QUIC on Chrome. And he actually says that Chrome actively detects when someone is trying to do that. And in that case, Chrome itself will block QUIC. They really, really, really do not want anyone looking and parsing QUIC. They don't want it to break in the future. So this tension is terrible. And this means that you will always, if you're deploying QUIC and H3, you will always need a secondary H1, H2 stack next to that as a fallback for people on these type of networks. There is a little bit of silver lining here, though, because QUIC itself is quite security aware as well. They've looked at what the main attacks have been in the past decades, and they tried to build in some of the fixes. For example, QUIC's version of a SYN flood attack is resolved by what QUIC calls a stateless retry. It's kind of an advanced version of TCP SYN cookies. It also tries to protect against UDP amplification attacks by saying, I'm only going to reply with about 3 times as much data as I've gotten, at least until the path is validated. This and many more things are baked into QUIC. So maybe we won't need that many middle boxes down the road, but we'll see if that actually matters in practice. Now, the irony here is that QUIC encrypts almost the entire transport layer, but at the same time, it adds a new field in the unencrypted plaintext header as well. And this field is called the connection ID. And this field is added mainly to help QUIC be resistant against NAT rebinding and also connection migration. And the latter is that if you're now on Wi-Fi and you would go outside, you would probably switch to your 4G modem. You switch networks, and so you also change your IP address. And TCP cannot deal with this at all. You have to drop all your TCP connections and reconnect. So what QUIC says is, in each packet in the header, we have this connection ID. This stays the same if you change networks, and so we can keep knowing that it's the same connection. Of course, if you do that, you will have just introduced the perfect fingerprinting vector for countries and large companies to track users across networks. So that's not actually what QUIC does. They are also going to change the connection ID when you do connection migration. And now you might be wondering, well, then what is the use? This won't work anymore. The way this works is that upfront, client and server are going to agree on a list of potential connection IDs that they both know actually maps to the same underlying connection. So that when you change, upon connection change, your network doesn't know that, but your endpoints still will. So that's good until you have an actual deployment on the web with things like load balancers. Because load balancers, they have to always route traffic from one connection to the exact same backend server, or things are breaking. You typically do that with a hash of the 5 tuple. Doesn't work if you do a connection migration, and neither can you use the connection ID. So how are we going to solve this problem? Well, 2 ways. The first is that QUIC actually doesn't have one connection ID, it has separate connection IDs for clients and servers. And both choose their own connection IDs that they allow the other to use. This means what the server, for example, can do is embed something like its own unique server number inside of the connection ID. So when you get a new QUIC backend into the load balancer, it simply has to look at the correct part of the connection ID, determine which server that belongs to, and send a packet on its way. Nice and stateless. And this is very flexible. You can actually do much more with this. For example, Facebook, they do 0 downtime upgrades, so they have multiple processes running at the same time, and they simply encode their process ID in the connection ID as well. Quite nice. Now, to make this work, you need a second thing, of course, because the load balancer and the backend both need to know the exact format that you're using in these connection IDs, right? They need to know which parts of these are going to stay the same if the things change and how to interpret that. And also, they might want to discuss how to obfuscate or even encrypt this, because you might not want to be leaking this type of internal state to the internet. So there's a proposal for yet another configuration protocol between your load balancer and your backend servers that kind of bootstraps you into this. So connection IDs, lots of fun, good feature, but can be quite complex to set up. And that is also true for the next feature, and that is QUIC's very fast connection setup. You might have heard this, TCP is so slow, it takes about 4 round trips to set up a connection, and QUIC is going to be much better because it can do all of that in 1 round trip. And that doesn't sound cool enough, so we're going to bring in that marketing department again, and we're going to call it 0 RTT, right? Now this is true. QUIC can indeed do this, but you first need to do something else. You first need to do what I would call a normal QUIC connection setup. In this case, yes, you can also do QUIC and TLS in one round trip, but then you need a second one for your HTTP level stuff. Now, in this first connection, you might get what is called a TLS session ticket. This thing contains encryption keys that you can then use for the next connection, right? So that's the way they can do 0 RTT securely, because they exchange new encryption keys up front. This is not something QUIC specific. This is TLS. This is even in TLS 1.2 in some cases. This is called connection or session resumption. But to do this in an actual deployment again has some problems, because the server also needs to remember those new encryption keys that you might be using. So 2 ways to do that. First of all, you might store all of these at the server. The problem is you don't know which of the backend servers your client will be reconnecting to, so you need to share all of these keys across all of your servers, which doesn't exactly scale. So the second thing, nice thing that you can do is actually defer the storage of these keys to your client. You can actually put them in the session ticket itself, have the client store it, and send it to you on the resumption attempt. If you want to do this securely, you need another encryption key. Let's call it the ticket key. And again, because you can do 0 RTT to any of your backend servers, you're now going to have to share this ticket key between all your servers as well. This means that you have now introduced a single point of failure into your setup, because if the attacker gets a hold of that ticket key, they can decrypt everything you did. So it's definitely possible to do something like this, but it has several challenges to do this securely. And it means that you probably should be rotating those ticket keys quite frequently. Typically, they say about once a day. This is good, but it reduces the effectiveness of 0 RTT, because if you come to the server a day late, you will be forced to go back to the 2 RTT connection setup. There's yet another problem with this, and this is called a replay attack. So 0 RTT is fully encrypted. Attackers cannot see what's in there. They cannot change anything. What they can do is intercept the message, make copies, and send them again to the server. So let's say that your 0RTT requests increment a counter, or, I don't know, move some Bitcoin around, right? You might see how that might become a problem. And so they say that 0RTT stuff can only be idempotent. It cannot change permanent state in the backend. Sounds simple, maybe, but typically that's something you have to enforce at the business logic layer, because even things like HTTP GET can actually change permanent state, depending on your implementation. So again, nice, cool feature, a lot of fun to implement, I would imagine. Now, I've been talking about setting up quick connections and resuming connections as if it's nothing. But let's try to see what happens if you try to set up a quick connection to a server that doesn't actually do QUIC, which is going to be most of them for quite a while. You can't wait until this connection has timed out, because that might take several seconds. So what you do in practice is you say, I'm going to start a TCP connection at the same time. I'm going to race the two connections. Whichever one completes first, that's the one I'm going to use. In practice, though, if you do that, it turns out that QUIC almost always loses. So what they started doing in several implementations is delaying TCP with about 100 milliseconds to give it a head start, and things do work. Now, this is not something new. This is what's called a happy eyeballs approach. Eyeballs meaning the end users, and happy because they don't have to wait several seconds for their connection to come through. This is actually something that was first introduced for IPv4 versus IPv6, because you have similar problems there. Now look what happens if we bring that into this. You can get this kind of situation. Now, I'm not saying this is what you should do, and I hope nobody does it exactly like this, but it does show some of the complexity in here in how to decide which of these connections to start, how to determine these timeouts, what kind of experience you might get. This also means that if you try to do this with 0RTT, you might be replay attacking yourself. Okay? So that's definitely something to keep in mind. Now, this is bad, obviously. So what we really want is to only try QUIC if we know that the server supports it. How we do that? If you have a new server, you've never seen it before, you're going to assume it does not do QUIC. You open a TCP connection. Somewhere in that connection, you will get what is called an alternative services indication. Typically, this is going to be in the form of an HTTP header. And in there, it's going to say, I do HTTP3, and it's at this port, and by the way, I also support these QUIC versions. So the next connection you do to that server is going to be QUIC. This is already nice, but it has problems of its own. Suddenly, we now need a cache of all the services that we've seen, and if they support HTTP3. We also still need connection racing, because we know the server supports this, but we don't know if our current network supports it. And so you might layer some things on top of that, some heuristics saying, okay, in this network I've already seen QUIC work, so it's probably going to work for this new one as well. But you can imagine how difficult that is going to be in practice too. The next problem is you still need to send a TCP connection first, which is not ideal. So one of the proposed solutions to that is, hey, how about we put that into DNS? So that when you fetch a DNS record, you also get the alternative services information, and you can do the QUIC connection immediately. Whether or not that's a good idea, I'm going to leave on the table. What I do want to say is that I can see this to be a big problem to actually test in practice. Especially if I want to do this locally, you want to test QUIC locally. I really don't want to have to set up a TCP server as well that does all services, or even worse, a DNS server. Imagine that. So, again, I promised myself, but I just had to. I think all services are going to be one of the major problems with QUIC in practice, especially for people not used to this kind of network protocol stuff. They're going to struggle a lot with, why is my stuff not doing QUIC, and how can I get it to do QUIC in practice? Now, it's not just this that is going to be difficult to debug. I think QUIC as a whole is going to suffer from this problem, because it's so complex and because it's fully encrypted. For TCP, you can probably get away with looking at it, for example, in Wireshark, because even if your HTTPS stuff is encrypted, your TCP stuff is, again, still plain text visible on the wire, and you can do a lot of stuff with this. That is no longer true for QUIC. To be fair, you can still use QUIC and Wireshark, but you need the decryption keys for each individual connection. Again, it's difficult to scale. So I've been working on this for over a year, And our proposal to do that is to introduce a single standardized logging format for the endpoints to use. So both the client and the server would output this kind of stuff, and it's really quite simple. It's just JSON. And it defines the type of events you can see in a QUIC stack, things like packet sent, packet received, but also things that you don't typically find inside of a PCAP or a Wireshark trace, and that are, for example, internal server state related to things like, let's say, congestion control, like the second event in the trace there. And I'm very happy to say that this has found some traction. Over half of all the current QUIC implementations actually output this format right now. One of them is Facebook, and they have been quoted to say that they are currently logging dozens of billions of QLog events in their production system. Dozens of billions. I hope you will forgive me this humble brag, but that is amazing. That is almost as many as the amount of bullets shot by Arnold Schwarzenegger in the Terminator 2. That's great. Of course, the reason for having this standardized format is mainly that we can now start building tools that work across all the different implementations. And that's something that we've also been doing. Our toolset is called QViz. You can find it at that URL there. And there are actually some demo files on the website as well so that you can jump in and start experimenting with this. So you can find visualizations like this. It's a sequence diagram that shows all the QUIC level frames going over the wire. And then on the left side also how this is impacted internal server state. Again, the things you normally don't see in network level logs. You also have some more advanced visualizations like this, where we plot how the congestion controller is behaving and how flow control is evolving, and that will help you to debug some of the, for example, slow downloads that you might be seeing. So this and much more to come at that URL. We hope to support this system for a long time as QUIC evolves, and that everybody can now much more easily get insight on what the protocol is doing, because we suffered with HP2 for a long time that it was just very difficult to try and debug things until web page test added what I showed before. Now by now, I'm almost done. You might be thinking, well, H2 was complex, but QUIC and H3 are also quite complex, right? So does the benefit outweigh the complexity? What is in it for me? And again, this depends on the source. Some of them say yes. They say about 8 to 26% lower latency, which in many use cases is really quite impressive. There are others, some example of user tests in academia. They say users usually don't even notice the difference between QUIC and TCP. And if they do notice, they don't really seem to care. There's also some proof that QUIC is relatively unoptimized at the moment, because all of the stacks actually run in user space instead of the kernel. Again, this is good to keep QUIC flexible and evolves quickly, but you might need a considerable amount of extra CPU power to serve the same amount of users you're doing for TCP. I realize that this doesn't really help. So the thing that I personally always try to keep in the back of my mind, and why I'm betting my PhD on QUIC, is this. And that is that Google and Facebook have actually been deploying this at scale for years now. Google has been using the initial version of QUIC, Google QUIC, for YouTube for several years. And Facebook has been running this new version, the standardized version, for over a year, well, at least the experimental draft versions of it, for over a year, from their native app to their actual production services. So they not only show that it might be complex, but it's definitely doable to deploy this in practice at scale. But the fact that they keep on using this also shows that they must see some benefits that indeed outweigh all this complexity. Whether or not those benefits are only visible at Google scale remains to be seen, but that's maybe a talk for next year. So by now, maybe you are convinced that this is a good idea, so what can you do? The thing is, you can start experimenting now. There are plenty of open source implementations that allow you to do that. I think you will be able to start testing on real systems somewhere around half next year, and then maybe have something in production by the end of 2020. So definitely a good point to start right now. The way to do that, I would recommend, is to use a CDN, especially Cloudflare and Fastly. They have been very active in this space. They have very mature implementations. Cloudflare even allows you to enable it already on their edge. If you are stubborn though, and you do want to run your own servers, there's also good news. Most of the popular server implementations have announced support, or they indeed already have support, or partial support, I should say, in some kind of open source form. If you want to get deep and dirty with QUIC, I would recommend the QUIC implementation. It's a high-level Python implementation, very readable, also very complete, very good to get to grips with the protocol. The only ones that are kind of lagging behind right now are the browsers, but they have also started showing some very early, very buggy experimental support in their development releases. This should, of course, improve in the next couple of months. So with that, I would say the main endpoint to this talk is, of course, go forth and reproduce. But before you do, remember to give us some feedback, either on Twitter or using the app or I don't know what. And then all that's left for me to say is, in case I don't see you, good afternoon, good evening, and good night. Thank you very much.
Got a few minutes for a few questions, if anyone has any. Oh, over there.
Hi. In one of the last slides, you mentioned the increased use of CPU for the users.
Yeah.
Well, since you're a scientist, do you think that the energy use is improved or actually or made worse?
Could you repeat the question? What use?
At the big picture level, the fact that you're maybe spending less time, that you've got less traffic in the network, but more CPU at the beginning and the end. Is it net positive or net negative?
Oh, this is actually like the amount of CPU needed for the entire flow. So even the positive points have already been calculated into these.
Okay, so it's really 9 times more energy.
In some reports, that is definitely not the main case. Some also say that there is no observable difference in certain use cases. So it's depends on who you listen to.
How come? Because kind of optimizing, so why would it use so much more energy?
So one, again, it runs in user space. So you have that. Again, it uses UDP. The UDP syscalls have not received the same amount of optimization as TCP over the years. So they're trying to fix that now, but for now, the UDP interface is actually quite slow. The other thing is that QUIC needs to encrypt at packet level. So in TCP, you can do TLS records that span multiple TCP packets. That's no longer true at QUIC. In QUIC, you need to encrypt each packet separately, and then QUIC also encrypts all packets twice. It encrypts the payload, and then it encrypts the header separately. So there's certainly some overhead from that as well.
Hey, thanks. A lot of those points were about like browser clients, but what about use cases in like for backend server-to-server communications over protocols like gRPC? I imagine you have much more control over the network, over client.
Yeah, very good question. So the thing is, especially the people from Facebook have been quoted to say that they don't think QUIC is going to be all that useful in the backend. So because it deals so much better with loss and the fast connection setup, it's mainly going to be better from the client to the edge, or client to the first access point. And then inside of the network, they don't really see all that many reasons to switch to QUIC. At least not now, because it's relatively unoptimized, so TCP makes more sense at that level. Maybe in the future, but at this point, they don't really see much benefit yet. But QUIC is much more flexible, so that'll probably change down the road. Any other questions?
Hello, thanks for the presentation. I just have a question about reducing the network overhead. Like, do you have any numbers on how much it can reduce the network payload, or?
I don't have numbers, but QUIC is exceptionally well optimized. The amount of overhead that you get is reduced to the absolute minimum. There is a crazy amount of incremental differential encoding being processed, and you have variable integers everywhere. So if you can encode it in 8-bit maximum, you can actually get away with that. It is hyper optimized at all levels to make sure that you have as little overhead as possible at the transport area. Anyone else? All right then, thank you all for coming.